Welcome back. What I want to do today is take a little peek at another gas law. You may remember we've already looked at Charles' law, which related volume and temperature, and we know that volume and temperature are proportional. As one goes up, the other goes up, and as one goes down, the other goes down. We also know we have to use the Kelvin temperature scale. We add 273 to the degrees Celsius, and if we do that, we're good to go. The next gas law we looked at was Boyle's law, which kind of dealt with the syringe idea where pressure and volume are inversely proportional. So when we squeezed down on the plunger, the volume dropped, but the pressure went up. That's assuming temperature stays constant. The last combination of variables that we're going to use involves pressure and temperature. And that gas law involves Gay-Lussac's law. There are many examples of applications of Gay-Lussac's law. Here is an aerosol can of paint. It's actually red engine paint for Chevrolet. And it's under pressure. You can see it. And of course, we know we should never throw these into a campfire because they can explode. And we know that's not good for the environment as well. So the aerosol can is under pressure. Assuming we have small changes in temperature, the pressure is going to go up in this can, but it's designed in a way that it won't rupture or break. A barbecue tank is the same. Don't put a big barbecue tank into a fire, or even a small Coleman's tank into a fire, because it might fail or explode. But we know, according to Gay-Lussac's law, that if the container doesn't explode, the pressure inside would increase as the temperature goes up, and the pressure would drop as the temperature goes down. So that's really all there is to Gay-Lussac's law. Let's take a look at it. Well, we go back to the kinetic molecular theory and remember that molecules are always in motion unless we get them down to absolute zero, which we've never really achieved in the real world. So, as we heat up a gas, we know that the kinetic molecular theory of those the kinetic molecular theory shows the molecules gain kinetic energy. That makes sense. So if we have a fixed mass of a gas inside of this container, and there is, it can't get in or out, it's fixed inside, and the volume stays constant, it kind of makes sense as we heat that canister up, or that aerosol can up, the pressure will go up. Graphically, it makes sense. There's certainly going to be a straight line, the slope would be constant, and P over T is constant. Therefore, the mathematical representation of Gay-Lussac's law is kind of similar to Charles' law when you look at it. Instead of using volume, we're using pressure. So P1 over T1 equals P2 over T2 at constant volume. And that's the key to this. Now, let's look at an example. Let's suppose we have our aerosol can here, and it's under a pressure of 138 kilopascals. You may recall that standard pressure is 1 to 1.3 kPa, or 1 atmosphere, or 760 millimeters of mercury. Those are all the same thing. Well, if it's at 20 degrees Celsius, which is a nice summer day, and we heat it to 50, which is very hot, the question is, what will happen to the pressure inside the can if the volume doesn't change? Well, we write down what we know. We know the initial pressure is 138 kilopascals. We know our initial temperature is 20 degrees Celsius. Don't forget to add 273 to get Kelvin. Very important. Our final pressure is the unknown variable. We're going to call that X. And our final temperature, 50 degrees Celsius, or 323 kelvins. There's our equation. P1 over T1 equals P2 over T2. Again, I think it's better, especially as you go higher in your science education, to rearrange equations before you plug the numbers in. We want P2, so to get P2 by itself, we have to multiply both sides by T2 and move that up. So P2 is equal to P1 times T2 over T1. You plug it in, 138 kilopascals times 323 kelvins, all divided by 293 kelvins, and we get an answer about 152 kilopascals. Let's look at it. Does it make sense? Well, I agree it does. Our temperature has gone up by a little bit in terms of kelvins, and you can see that our pressure went from 138 to 152. This looks good to me without doing a check beyond that. That's it. That's all we have for Gay-Lussac's law. Pretty straightforward. Plug it in and solve. The next step in our journey in the gas law world is to look at a more realistic situation where pressure, temperature, and volume can change. Because technically, if you really think about it, Gay-Lussac's law is a bit utopian in a way, as is Boyle's law, as is Charles' law. If I heat this can up, no matter how little, technically its volume will change just a little bit. And the same goes for Boyle's law. When we use a syringe or a plunger, like I've already shown you, technically the temperature will change because of the friction inside. And of course, a piston in an engine is a good example of that. So there are some more complex problems that we can work on when all three variables change: pressure, temperature, and volume. And that'll be our next stop, and that will be known as the combined ideal gas law. I hope this helped. We'll move on to the combined gas law next.